Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
I will start as well. A couple of admin things first. There's yet another brand new tutorial, of which one person's found it already. It's actually a good time. It's Thursday at 10 o'clock. If you really like these Thursday at 8 o'clock in the morning, that's up to you. Wouldn't catch me there. So if you want to, you can probably change into that tutorial, but there's about 14 people sort of waitlisted at the moment who will probably get into there quite quickly as soon as they get the announcement. The other things I've made as course announcements are here. So the more GLM's tutorials now available. I've put up something there for people who might be interested, who are actually doing a stats major or something where this course is actually compulsory for them. Might be thinking about becoming a statistician. Bit of career advice there. Came across my desk while I was away. I'm finally getting through my pile of about 5,000 email. So I came to it earlier today, so put it up then. If you've got any other problems with the course, the admin side of things, if it's about degree or course enrolment, start with the college office. If you need admission code, then you have to talk to Adam Butt. We don't get the ability to hand out permission codes delegated down to my level in this school. It's all, I have to send it upstairs, so you might as well talk to Adam direct. That probably doesn't apply to anybody who's actually sitting here because you're probably already enrolled. If your questions about tutorial enrolment, then read this very carefully. Don't contact me, you'll just annoy me. Contact the school office. Save us both some time and go direct to the only people that can help you. And if you're really not sure about it and you're worried about annoying me because I've obviously been a complete grouch about things, ask Tim. Okay, we're going to pay him some extra money for this aggravation. There's about 190 of you now, so that's enough to sort of mean there's a lot of annoying admin to do. My job's to teach statistics as far as I'm concerned. Okay. So the tutorials, I've made them so that these tutorial links will work for a couple more days. They were supposed to shut off at about 5 o'clock today. So if you want to rearrange your tutorial enrolment, you can do it up to 5 o'clock on Wednesday. After that, you will have to see the office. Okay, so where are we? Well, what I'm hoping is, because of last week we had a couple of extra tutes to help people who'd never used R before get started with R. If you just turned up for the first time today, because you thought the first week of lectures is always optional, well, sorry, it's not. You were going to have to help catch up by yourself. Last week we handed out some help with catching up. Okay? So if you're not up to date with statistical computing, i.e. you can't get through most of tutorial 0 without any problems, but actually a better test for whether you know enough R is whether you're able to do tutorial 1. Which is the revision tutorial. So if you haven't started reminding yourself how to use R, please start putting some work in now. The second section here is the revision stuff. The other thing you're supposed to have done before you got to this course is to have done regression modelling. Hopefully recently for most of you, this year or last year, and we've been going through what you should know from that. I'll have a little bit more of that today. I'm going to go through these slides I didn't get a chance to do last week. I've read a couple more things, but notice that the highlight is now on the first topic of the course proper. So you should start by having a look at the brick. The first 10 pages of the brick is a fair bit of mathematics for most people. So what I'm going to try and take you through today is a slightly less mathematical approach. I'm going to sort of start things by looking at the example and the nitty-gritty of the example in R, and then we'll come back to the bit of maths you need to know that R is doing in the background. Okay? Your homework, yeah, I'm sorry about that, rude word, isn't it? Your homework was to actually have a quick look at these two things. This course isn't a course about experimental design. We do teach a course about experimental design, Stat 3012, and I can't remember the graduate equivalents. But the whole point of this first section is that these linear models we use in regression modelling are also used to analyse design experiments. Okay? There's a couple of differences, and we'll get to those in a second as we start the material for this week. But there was also, which I'm going to do every week, I'm going to put the workshop up about Wednesday of the week before, Thursday if I'm getting a bit pushed for time and like, and you're supposed to have a look at that before you come. That's what we're going to go through at 5 o'clock. Today wasn't that much to do for the workshop because we haven't actually done the stuff you need to do most of the modelling. I'm about to try and do that about now. But I did want you to at least think about the issues, think about what it means to be a designed experiment, because this example is an example of a designed experiment. And we need to do things like we did for the ordinary regression models. We need to be able to identify the research question. We need to sort of think about the nature of the data we're dealing with. And that was the homework. So that was in workshop 2. And, okay. So, I don't use slides that much. Here are some slides I did for... This has got enough juice in it to actually last a while now. Okay. I apologise for my fellow lecturers, we can't put these things back in the right place if the sound goes. Okay. So, regression modelling. These were some slides I did for the last time I taught regression modelling, which was first semester of last year, not this year. Paul Anton had first semester this year. And just remind you how we used to describe what we call the general linear model or the multiple regression model. It's just a linear combination of a series of random variables and some coefficients, i.e. a line if you're in 2 dimensions, a plane if you're in 3 dimensions, a hyperplane if you're in 4 or more dimensions, mathematically. And it's got a deterministic part and a stochastic part. And in matrix notation, it's actually fairly easy to describe. Trouble is, a lot of you haven't actually done any linear algebra. But some of the matrices that R fits for us in the background are going to be key parts of this course. So we're going to have to at least talk you through a little bit of linear algebra so you can understand what we can get out of some of these matrices. And in matrix notation, it's a lot simpler. So, what we've got is a vector of coefficients, and we've got a design matrix, which is a 1 that holds the place of the intercept, and a series of variables, x1 up to xk. Okay, and we've got observations, n observations for each of these variables. Okay, and remember the interpretation of a partial regression coefficient is the expected change in y as the corresponding x changes by 1. That was the slope coefficient in a simple linear regression. In a multiple regression, we were saying that all the other x variables are held constant. So beta 1 is the expected change in y as x1 changes by 1, with x2, x3 up to xk held constant. Trouble is, in an observational situation, you typically can't hold the other variables constant. They're interrelated to some extent. As one changes, the others will change as well. which you probably found in multiple regression. And notice we talk about this model being linear. It is linear in the parameters. It's linear in the coefficients. It's not necessarily linear in the variables. So that's a quadratic, mathematically. Okay, it's a parabola. It's a curve. This is an intersecting plane. You've got it in 3 dimensions, x1 and x2. You've got the product of x1 and x2 there. It's not linear in x1 and x2 because there's that multiplicative term in there. But it is linear in beta 0, beta 1, beta 2 and beta 3. And both of those two are examples of polynomial regression of some sort. Okay, and even things that don't at first appear linear can be linearized. So we saw with the black cherry example last week that we took the logs of both sides, we turned something that was obviously not a linear relationship into something that was linear on the log-log scale. And you can linearize other relationships in a similar sort of fashion. In fact, the log transformation held a pretty key place in regression modelling because it was an example of a transformation that could be both linearizing, i.e. turn non-linear relationships into linear ones, and variance stabilizing. You could stabilize the variance by affecting different parts of the range. The log has a larger effect on the larger values than it does on the smaller values, and it can typically stabilize situations of increasing variance as a result. So the log transformation is an example of a linearizing and variance stabilizing transformation. Often one of the first things we'll try if we're going to try an empirical approach where we try these things out and see if they work. The model assumptions were that the errors are independent, identically distributed with constant variance. And there's that constant variance down the sort of the diagonal of the variance covariance matrix. And it's a variance covariance matrix because between different observations there is arguably no correlation. The observations are supposed independent. In other words, these off-diagonal elements are all 0. Okay. And we did note that when we do these sort of things, we can assess all of these things by still drawing just 2-dimensional plots. We can draw plots of the residuals, standardized or preferably standardized, against the fitted values, because the fitted values are a function of all the x variables. In other words, once we've estimated the coefficients, the parameter coefficients, we've got a known or fixed combination of the x variables, which are also supposedly known. So therefore the y hats in a sense are known, the y's are unknown. We can plot the known against the unknown and see how good the relationship is. Or better yet, we can plot the residuals, because the residuals are the deviations away from the model, and the residual plot blows them up so we can see what's going on. And we saw that we saw somewhere in regression modelling that we could estimate this coefficient of parameters using least squares, essentially by minimising this variance function here. Okay, and the betas that came out of it, and essentially the constraints we had to satisfy in that minimisation are shown there. And we've got our obvious estimate for the thing we don't really know, which is the error variance. That was that key variance parameter. So remember, back in this model, here's the deterministic part. Everything in there is assumed known. Well, it isn't known by the time we estimate it here. These are like fixed estimates of these. These x's are assumed to be measured without error, or at least with negligible error compared to y. So the last little bit here is the stochastic part. It's the variation around the model. So we've got a deterministic part and we've got a stochastic part to our models. And our stochastic model is best summed up by, or best estimated, the key variance parameter in it is estimated by this. Okay, so that in a nutshell was what you should have known for from regression modelling. I've added a couple of other things there. I should have put non-examinable on these because I'd like you to read these sorts of things and anything I sort of throw at you. I'd like you to be good stat students who are trying to learn a little bit more about what we do as statisticians. And this is a good, thoughtful article on taking a step back and sort of say, look, how do we use statistical models to answer research questions? But probably more pertinent is this. Is these quotes from George Box, somewhere down here. That one there. Essentially, all models are wrong. They are at best some sort of approximation to what's going on, but some of them are useful. Okay, so the whole aim of statistical modelling is to try and get ourselves into the class where we've got a useful model that can tell us something about what's going on. Okay, we want to rule out models that aren't useful, i.e. could be misleading because the underlying assumptions are not followed. So the reason we check all these residual plots is because we want to be sure that we've got, first of all, an appropriate model. Even if we've got an appropriate model, i.e. one where the assumptions seem to be okay, it may not necessarily be a useful model unless it's something in it is significant, suggesting that there is something going on. Okay, we can still model quite happily without violating the assumptions a relationship, a non-relationship, a spurious relationship, but we want to be happy that we've also, seeing something in the model that is useful. Okay, so how do we do that in a slightly different context? So what I'm going to do now is move on to the stuff that's in the beginning of the brick, and now I'm going to slow down a bit because up to now it's been revision. You're supposed to know this already. You weren't supposed to forget at the moment you walked out the exam for regression modelling. Okay, so hopefully, if you're trying to do this course the right way, you've had a little look at the lecture notes. You might have got a bit confused. Hopefully we're going to solve that confusion now. Hopefully you've done a little bit of reading like that, the little book I put up there, my comments on experimental design models, and maybe had a quick look at some of these things that give you some of the jargon in experimental design. I have to apologise here. I have been doing some of this stuff since the mid-1980s. So very so often I'll use the jargon and I forget to define it as I go. If I do that, please stick your hand up and ask me and I will try and fill the gap. Okay? But because I'm so comfortable with this jargon, sometimes I just use it. Okay? Part of your job as apprentice statisticians is to sort of learn some of this jargon as we go. A lot of it we'll learn by osmosis, i.e. you'll sort of see things in context, look them up, and get some sort of definition of them. These two resources here aren't bad ones to have a look at for well, the Montgomery one is really just a quick extract on some of the buzzwords used. Alan Walsh's stuff is actually a little bit more deeper stuff about some of the ethics of issues involved in doing experimentation. Wonderful materials. Let's see if I can. Thank you for that. Okay, so. Well, the way I want to motivate this is by actually not starting into the brick. I want to go back and have a look at another example that isn't in the brick. The reason it's similar to some examples you would have covered in regression modelling. It's about indicator variables. So I think who can remember what indicator variable was from regression modelling? 0, 1, yeah. Okay. So it's basically, it's the easiest sort of categorical variable to code. Because basically we can code as a 0 if it's not this thing, and 1 if it is. So if we sort of create a variable like sex or gender, you can sort of say we can define males as 1 and females as 0. Although I usually like to do it the other way around and describe males as 0 and females as 1. So this example here, I'll just run you through I had to put the explanation for the data here because I hadn't anywhere else to put it. I should have probably done it as a case study sort of thing and given its description elsewhere. This one is an example that's, I think it's concocted. I hope it's concocted because it's in one of the classic texts in multivariate analysis. It's about a savings and loan bank in the US, and it's data on their 116 bank employees. Okay, we've got an employee ID, we've got the sex, 0 equals male, 1 equals female. We've got the age at hire in months. It's a count variable. It's actually a discrete count, of course, because you count the number of months in exact months typically, not in parts of month. But really it could be treated in a lot of situations as a continuous variable. If there's a large enough number of values in the range. Years of education, same with that. It's really a count variable. Level of education. Graduate school, college graduate, some college, high school graduate, none of the above. That's a categorical variable. I probably won't be using that one in this particular example because we've got to sort of do some work before we get to those. Work experience in months, starting salary in dollars, seniority, total number of months of employment, and salary, current salary in dollars. Most of those are actually all count variables. Okay, so they're not the nice continuous stuff we were used to dealing with in regression modelling. We did find in regression modelling that we could quite often do something like put a bunch of percentages into in as a variable and still get reasonable results as long as we had enough values. Essentially what we were relying on there. So think about a percentage. What's wrong? A percentage is actually a good example of a variable that you probably shouldn't treat as a continuous variable unless it meets certain criteria. Okay, so what's wrong with a percentage as a continuous random variable?
It's an integer.
Sorry?
It's an integer, so it's discrete. So
Well, it's arguably discrete, but like I said, if there's enough values, that's probably not an issue. Is it bounded? Yep. You don't get much. You don't go below 0%, and you go above 1%, do you, 100%, do you? Okay. What really should you be modelling a percentage with? Think of it as a 0, as a 0 to 1 variable rather than a 0 to 100% variable. It's certainly on a range from 0 to 1 or 0 to 100%, but who remembers the binomial distribution? Okay, so in fact it's really a binomial proportion when you think about it. It's the percentage of people who said yes to this, or the percentage of, it's really binomial in its nature. Now, so in that sort of sense, if we are going to treat it as a continuous covariate, what are we relying on? We're relying on its approximate normality in certain situations. So anyone who remembers the normal approximations of binomial from first year? Okay, so what are the limits? When shouldn't you use the normal approximations of binomial?
Usually the cutoff is about.
Well, yeah, I mean,
But I think that's something else.
well, first of all, yes, you want n to be reasonably large. You want to have a fairly large range of values, but you also don't want to be too close to the boundaries. You don't want to be too close to 0 or 1. As long as you're talking about a reasonable range of values and you're not getting too close to the boundaries, you can probably, the normal is a good approximation to the binomial. Okay. These things are actually probably Poisson counts more than anything else, but again, there's a normal approximation to Poisson that works, again, as long as we don't get too close to the boundary. But the possum, there's only one boundary, it's the zero count. Okay. So, what would we do with these data? Well, we'll read them in. I'll make them available on Wattle, like everything else. I've just got to click a couple of things to... Here's the data. There's a lot of them. There's 116, so it's only giving me... It's missed out the last 5 rows. There's the variable names. I'm going to attach these so I can use them by name. And the research question here is actually, is there any discrimination in the salaries given to males versus females? So in fact, one of the key explanatory variables here is going to be male-female. In fact, that is not... It's a Bernoulli, it's not a binomial, it's just a 0-1. Okay? So we want to see how, but we have seen, if you remember in regression modelling, we actually see we can implement 0-1 variables in these models and get sensible results for them. Here's the mean overall salary. Here's the mean salary for, which way did I code it? That's the mean salary for males. Here's the mean salary for females. Is that by itself evidence of sex discrimination? What do you have to control for? All sorts of things. Seniority, seniority is sort of, code for length of prior experience or length of or how long they've been working there, what level they're at, how much education they had, their starting values, and various other things. Okay. But notice what happens if we do just a naive linear model of salary against sex. And plot it. What's the first thing you notice? This is a residual plot. This is the main residual plot of the observed values versus the fitted values. Okay. Notice this value here, 1050. We can actually see it over here. These are all the females, because the fitted value for them is their average value, their average salary. Here's the 13092. These are all the males. Their fitted value for all the males is basically the average male salary. So basically it's modelling these things in terms of their means. Okay. What's another thing you notice about this plot? Yeah. That number 9 looks like a Y, doesn't it? My suspicions here are number 9 is the son-in-law. There's been a bit of nepotism in this company. Harry's Savings and Trust, Harry Jr. has been employed. Okay, and getting a commensurately very large salary as a result. What's the other thing you should try to do from a residual plot? Well, first of all, here's the model, and the median smoother is suggesting there's a bit of a departure of the model from the data. Okay, maybe Harry's inflated things so much that he's drawn the model towards him, and if you like, we're departing from that. The median, because this is essentially a median, well, it's a lowest smoother, but it's closer to a median smoother. That's probably going to be more robust to the effects of Harry Jr. as an outlier. Okay. I should be able to try and assess constant variance on these sort of plots, shouldn't I? Kind of hard, isn't it? The two groups look about as variable as each other, except for Harry Jr. Okay, If you were taking the range as a proxy for your measure of spread, then Harry inflates that badly. Probably also inflates the variance for that second group. But in a sense, the spread here and the spread here seem somewhat similar. Okay? So that's what we try to get out of these residual plots, and we're going to try that a lot this semester to try and get what we used to get for regression models out of plots that don't necessarily play ball. Here's a normal quantile plot. Actually pretty good, because really most of the normal quantiles are following the line quite well. Again, number 9 seems to be a pretty extreme outlier, distorting the plot. I'm not going to worry about that one at the moment. I don't think it tells you much more than you can get from the first one. And here's your outlier plot. And yes, observation number 9 has got a Cook's D of somewhere between 0.5 and 1, which are the arbitrary limits used on this plot. Okay, let's have a look at the features of the model there. Here's the analysis of variance table, which I probably shouldn't go to because I know there's problems with this model, so therefore I probably shouldn't be doing, this sort of analysis on it, because I don't think I really have an appropriate model yet. But it's suggesting that there is something going on between the sexes, i.e. sex is a significant contributor to this model. It's a significant term in the model. Notice this is equivalent of a simple linear regression model. So when I do, when I do the summary, I should get a very familiar notice the p-value is very familiar because the t-test here is the f-test is the square of the t-test. Okay, so if I square that, I'll get 23.714, and I get the same p-value. Okay, that's what remember that used to happen with simple linear regression models. Essentially, the f-test on the overall model for a simple linear regression model was directly equivalent to the t-test on the one slope coefficient in the simple linear regression model. Okay, these estimates, what are they? Well, there's the intercept. It's the mean salary when sex equals 0. Because really we have code this as a 0, 1 variable. So when x equals 0, beta 1 times x disappears. All we've got is the model, the fitted model equals the estimated value of beta 0. Okay? So the intercept is basically the value for when x equals 0, and the slope coefficient is the difference between the two. Okay, so let's draw that up. Because this is going to be key to understanding how we're going to code categorical variables in general. We're going to use a series of these indicator variables to indicate the different levels of the categorical variables. So let's do it in the simple case where we've just got 2 levels, and then we can extend it later on to more than 2 levels. So really, what we've got here is we had a whole bunch of, if we're looking in terms of the sex, In terms of the sex, the males are actually down here, and the females are here. Okay, so in fact we're going to, it's the reverse of what we saw on the residual plot. We've got a whole bunch of males here. We've got a similar sort of cluster over here. I'm going to exaggerate the slope a bit for the females. And we've got observation 9. The overall mean, which is actually quite high up in this group, it's not at the median because it's been inflated by the presence of observation 9. This is going to be beta naught hat equals 13092.20. The average salary for males. Okay. Over here, if we go 1 in this direction, remember what the definition of the slope was? It was how far we had to go to get to the slope was the expected decrease, in this case in salary, as we go from 0 to 1, as we go 1 in the x direction. So this is basically 1, and the difference here to the middle of this lot, this is beta 1. In other words, this is how much we have to go down to get back to the line, to get back to the regression line. In fact, here's the regression line. It goes through beta naught, and it's got that slope, beta 1. As you go along 1, it drops by this much. And the difference is beta 1 hat equals minus 2590.5. Okay, so that's what it's actually coding up. So you can see how the model coefficients relate back to the situation we've got. They are really modelling the means of the two groups. And so the question is there a significant difference between the two groups? How would I answer that? I mean, forget first of all, this model is not appropriate because we've got an outlier in it. Forget that it's probably not appropriate because we haven't controlled for all the things we should control for. But if you really wanted to try and use this model to try and answer our research question, what should we do? We've already seen the t-test, haven't we? Yeah. What's the result? Was it significant? Yeah. So this model is saying there's a significant difference between the salaries for males and the salaries for females. However, that's not the right answer, is it? Because we haven't controlled for things and we haven't got an appropriate model. But that's exactly what we get if we did a two-sample t-test as well. So the two-sample t-test is assuming equal variances, which you probably did in first year sometime. This simple linear regression model, which assumes equal variances in all the groups, is directly analogous to that. So what we're saying is that y hat equals beta naught hat plus beta 1 hat x equals beta naught hat plus beta 1 hat, and x here really is a dummy variable for sex, an indicator variable for sex, where d sex equals naught if male, 1 otherwise, and the only otherwise we've got here is females. Okay. Remember, this is a 1977 example. These days we probably have to account for more the possibility of more than two sexes. So the model for males, where d sex equals 0, is y equals beta naught hat, because d sex equals 0, x equals 0, that term drops out. And for females, d sex equals 1, we have y equals beta naught plus beta 1 hat times 1 equals beta naught plus beta 1 hat. And so if we take beta naught, and we add beta 1, what we should get is we should get the mean salary for females. Okay, does that make sense? Good, because we're going to have a lot of that this course. We're starting on the basis of how we deal with categorical variables. Okay, well, back to the example. Notice the t-test on the, assuming equal variance, is exactly the same. Got the same p-value. It's got the same test statistic as the standardised slope coefficient. So the two-sample t-test you did in first year on two groups would have given you exactly the same answer. Because really we're making the same assumptions. We're assuming equality of variances. Notice if you did have a good first year lecture, they probably should have said you shouldn't assume equal variances. We should at least check first with an F-test whether the variances are equal. Notice that treatment coding is not the only way we could have parameterised this. We could have set up sex this way. Okay. So, looks like a pretty similar coding for all the females. But notice for the males, what it does is it says the males are the reference group. What we have is we sort of set up our parameters so that they add to 0. They sum to 0, and so we set the reference category to -1. So sex 2, the male, if sex was 0, i.e. male, we'd set it to -1. If it's not male, i.e. female, we set it to 1. So 1's the active treatment, and if you like, -1 is the reference category. That's how sex coding works. I'll come back to, some coding works. I'll come back to that when we look at a more general thing. But if I did that one and plotted it, what do I get? Does that look familiar? It's pretty much the same residual plot as the previous one we had. Okay. All I've really done is I've just changed the information slightly. I haven't actually added any new information. I haven't made substantive changes to the information. All I've done is recode it. So I've been consistent in my recoding, and everything that everything that used to be a 0 is now a -1. It's the same information in a slightly different disguise. It's called a different parameterization. And under a different parameterization, I really get exactly the same model. And I'm certain it's the same model because I can get the same residual plots. However, does the analysis of variance table change? Well, I'll give you a hint, it hasn't changed at all. Because really, the different parameterizations are the same information coded the same way. The analysis of variance table is sort of like robust to that sort of change. It really is, this summary, the variance summary of the model is exactly the same as it was before. What about the mean summary? Has that changed? Ooh, those numbers don't look familiar, do they? Let's have a look. Here's the overall mean salary. Unfortunately, the intercept is not that. It would be that if we had some nice feature in these data. Why is it not equal to the? Why is the the intercept not equal to the overall mean. And that's really what we're trying to do here, is we're trying to set up a set parameterization. But what we do is we model the overall mean for both sexes, and try and model deviations away from that. But it's not the overall mean. Why not?
It's because there is a disparity in the amount of women and men.
There's more men than there are women. I said there's more. She's the other way around. I think there's more women than there are men. Yeah. It's an unbalanced design. We don't have the same number in each group. So in fact, what you do get, it actually turns out to be the average of the means for the men and the means for the women. So it's basically the simple average of those two means, and that's what it's given me as intercept. And notice I could get back if you add that to this, you get to the average for the. Adding that to that is actually subtracting 1295 from that. You get to the mean for women. You add the negative of this, and you get to the mean for men. So that's the mean for men. And if I actually did the other. That's the mean for women. Which I do a bit further on. Okay. And notice I can just check that by looking at what the means are there and there. Okay. So yeah, again, this model is just a slightly different way of describing the same information. It's called a different parameterization of the model, but it really just contains the same information. It is still modelling things in terms of the means of the groups. So we'll come back to that in a big way when we get to more complicated examples, because it's keen. But let's just have a think about what we really should do here. And this is actually, I'm following what they did in the textbook here. I'm not sure I actually totally agree with it. So, but who am I to argue with Doug Carroll, one of the gods of multivariate analysis? So here's a model for starting salaries. And the things he reckoned they should be controlling for there were sex. Well, you need to have sex in there because, if you think about it, that's actually the research question here, isn't it? We need to know if there's a difference due to the different sexes. So we have to have sex somewhere in our model in order to test for that. But the other thing we probably should control for, and I would probably do it the other way around, by controlling for those first and ending in sex, because the trouble is when we don't have equal numbers in the two groups, we're going to have non-orthogonal contrasts. We probably should do our controlling variables first. So I certainly would have set these models up slightly differently, but we'll get to that as we go along. So the things he sort of said we should be controlling for in starting salaries, we should be controlling for how much work experience they've got, previous work experience they've got, and how much education they've got. Both sounds reasonable, doesn't it? So let's have a look. Okay. Now, a more reasonable looking residual plot now, because we've got more values of those work experience and previous education. Notice in fact we do again get certain combinations, so we get some sort of vertical lines in the plot still. But I mean, and the upswing here might just be a lack of data down this end. Okay, we've already got a very few trainees being employed. They're people with low education and low work experience. There's only so few of them. I'm not sure. It might be more an artifact than anything else. The rest of it looks pretty good, except we've now got a different outlier. Okay. Wasn't observation 9 anymore. This one is somebody who's getting much lower starting salary than they should do under the model. Okay? And it might have been enough to perturb the model towards them a bit. Is there any other problems? No, the normality seems pretty good. Trouble is we've again got the outlier there. And yes, it appears there's an outlier there. Okay. Now here's where I definitely would have disagreed with Doug Carroll and Co. Because they did actually publish this. And I think they probably should have solved the problem with the outliers first before they did this. But here it's sort of saying that yes, sex, work experience, education are all significant contributors to this model. Notice it took 1 degree of freedom to fit sex, which is a 0, 1 categorical variable. We needed that one dummy variable to fit sex. We've got that one indicator variable for there, and we've got slope coefficients for these two. We probably should check. We should at some stage have checked that work experience education years had enough values that we could treat them as continuous, but we haven't. And here's the summary. And what does that negative coefficient on sex suggest? Well, first of all, what's the positive coefficient for education of years suggest? Each additional year of education tends to up your starting salary by about 200. Okay? Each additional year of work experience tends to also increase your starting salary, but not as much as the extra education. Being female rather than male tends to depress your starting salary. Okay, we'll that's ignoring the problems with the model. And it turns out observation 88 turned out to be the only college graduate out of all the 116 employees. So this was a Midwest bank, and they didn't employ college graduates. So she actually had a remarkably, the model was suggesting that, with her work, with her education, she should have been right up the top. Okay, by the starting salary theme. But obviously she was a college graduate who decided to work at the bank for different reasons, and didn't attract the starting salary of education, which suggests she should have got. We possibly should have excluded her as a separate case, given that she was the only one of her characteristics. Okay. So here's the excluded one. I'm just doing this because I didn't agree with Carroll and Co. what they did. So I'm just excluding observation 81. Do we have a reasonable? Doesn't look too bad. Here's the analysis of variance table. And here's the summary. Even excluding observation 81 is suggesting there's still a significant drop in starting salaries for females compared to males, controlling for education and previous work experience. So do you have a question?
I was going to ask, so with regards to treatment of the outlier 81, you were talking a lot last lecture about experience and someone coming to you with a problem. So in that situation, you go back to the person that gave you this question.
Well, what I do with outliers, I wouldn't throw them out on the belief that the data is wrong.
You get non-statistical means.
I would basically try and do what I could to confirm what was going on with the outlier first. And that means if you're actually working with a client, and you go back and say, look, what was different about these data? You find some sort of rationale. You may end up excluding maybe the appropriate treatment once you've gone through all the other options. But there are a whole heap of other things. The ADF still uses a macro I wrote from the 80s called Windsor. Windsorizing basically reduces the value for a particular outlier. I'm not sure I agree with that either, but I was a junior who coded it up for them. And they still ask me about it occasionally. But yeah, there's other things you could do about outliers, but the first thing you do is work out why they're an outlier, if you possibly can. Trouble with a lot of econometric models is typically it's working on data that's been collected and published, sort of stock market data in finance, or you're dealing with sort of, things off these databases. There's no way to go back to the original thing, and you may have a reasonably strong belief that this model should work in these situations. A lot of the finance models, everyone's fitted these, we should be able to fit this in this situation. And so if you've got a strong belief in the model, then you start removing observations. I think there's a limit to what you can do in that direction, though. You know, you start throwing out enough observations, you can make any model you like fit. Okay, but good question. So this was the Latin Carroll and Green's model for current salaries, was based on sex, what they got as a starting salary, their work experience and education years, and their seniority. The seniority is how long they've been in the company. So the longer you've been in the company, presumably the further your salary's got from your starting salary. So all of these, again, are sensible things to control for. Let's have a go at that. Okay. Son-in-law's back. His salary is just a bit too big for what it should be, given all the other things you're controlling for here. Here's the analysis. Oh, sorry, I should do the rest of the plots first. So there's an all-quantile plot, scale location plot. There's the outlier plot. Okay, just below 0.5, which is why you don't use that criteria. It's arbitrary. This is an outlier in the sense it's outlying away from the rest of the observations. You know, I'd be treating this regardless of whether it passed that arbitrary criteria or not. Do not be tempted to use these things as hard rules of thumb. And analysis of variance table. Okay. Now you can tell we're in the realm of sociology because we're accepting things at 0.05 and a bit. All else fails, but actually alpha. So I'm being cynical here. I'll give you a bit more guidance on that later on in the semester. Work experience seems to be important. Starting salary seems to be highly important. And sex also seems to be important. By how much? Let's have a look at the coefficients. Again, assuming we can actually use this model in this way. Control enter. Okay. Well, it's suggesting that being female retards your salary by $1,300. Again, we've got problems with outliers. We probably should do something about them. We should be fixing them. I probably wouldn't have gone with, like, if I'd been Latin Carroll and Green, I'd have probably done some more work in this data set before I put it in there as a student example. Okay. So the points I'm trying to make there is that we can sensibly code up a two-category variable, a yes-no, true-false variable, male-female. These binary variables can be coded and can be readily interpreted in regression models. Hopefully that's all the messages you took away from regression modeling in the first semester. Okay? They have ready interpretations. The interpretation depends on the parameterization. Okay? So when you get to the summary table, you've got some extra work to do to work out how do you actually code these variables. But for things like the plots and the analysis of variance table, the coding is actually, the parameterization is actually pretty irrelevant. You can at least assess the basics of the model before you do that. So when you want to sort of make specific assertions about how much has this affected somebody's salary, that you have, and you want to actually interpret the actual coefficient of the model, you need to worry about how it's parameterized. Okay. And we've seen two different parameterizations. We've seen the dummy variable parameterization, and we've hinted at the sum parameterization. We need to put a little bit more meat on both of those. And that's what the BRIC tries to do in a fair bit of mathematics. If you've done a bit of maths, or you're happy to read through that sort of stuff, the BRIC's example is not bad. The BRIC's rationale is not bad to work through. I find that most people work through it a bit easier once we've actually gone through what it means to know our example. So that's what we're going to do now. And that's why the next workshop is essentially this corn data. Okay, I need about a minute's rest here to let my voice settle down, so if you need to go quickly to the toilet or something, now's the time to do it. my voice.
Sorry?
This is the rest of my voice, but yes. Okay.
Could you start removing the ones that are not significant?
Little depends on the argument you're trying to make with these models. Should we be controlling these things? Okay. Are they non-significant because we've got so many other problems with the model? Okay. Should we first of all fix the problems with the outliers, and then decide on the significance of the variables? Now, I typically tend to work on these models from both directions. You know, I do have a sneak peek towards the end and sort of see what's going on, and sometimes that guides what I do. But most of the time, I try to be systematic and sort of say, look, the first thing I should do is get to the main residual plot. Okay, and that means possibly a transformation, possibly a treatment of outliers, investigation of treatment of outliers. All those things probably come ahead of actual model refinement. I'll work on the final list of variables once I've got all those issues first. But even then, if I've got a strong belief that these things should be in that model, then I probably don't keep it within a control for them even if these variables.
So you're allowed to do that? Like you can just leave them?
Yeah, you are. But I think it's a research finding on the way that we thought we should control these, but it turns out it wasn't as much important. It's a sort of a non-result. Okay, I'll start again in about 2 minutes' time, so... Well, that's what I was just talking to the other question about there. They're insignificant at the 0.05, but first of all, I should have decided whether I was going for 0.05 or 0.1 a priori. Okay. And secondly, I'm not sure I've got a good model yet because I've got problems with outliers. So before I decide on whether I'm going to refine those out of the model, I should decide on the issue of is this the right form for the model first? You know, so I work through the assumptions, from sort of from independence. In other words, in terms of the residual plots, I get the main residual plot looking okay, because then I've got an appropriate model. Then I can start talking about is this the right model, given is this an appropriate one. Yeah. So and look, it's not necessarily the only way to do it. Okay, there are. Yeah, but the correct process will differ depending on your interpretation of the situation. Okay. What you're looking for still is you're still looking for a useful model. A model that tells you something about the situation, given the assumptions you're making. Now, one of the assumptions I'm making is that, it might be vitally important to control for these things. In which case, leave them in even if they're not significant. And what you've got is you've got a non-result. Even though I thought it was important to control for these things, they turned out on these data, on this particular sample, not to be important. Okay, so there's a difference in how you sell the message. You don't automatically just go, no, hard and fast rule, get rid of it. I'm sorry, things aren't black and white. It's a grey area here. Okay, I probably should start again, even though my voice is not holding up very well. So, about 10 pages in, page 6 and 7, about 6 pages in, after a fair bit of stuff about describing indicator variables and coding for categorical variables, you get to the first example in the book, in the lecture notes. And it's here. It's a A classic agricultural experiment. What do you think the research questions? So first of all, who's had a look at this? Who's done some homework? Who's read the stuff that they've asked them to read?
There wasn't a source data.
Sorry?
I couldn't find the source data, and then he said, yes. You don't know the original source data?
I don't know the original source now.
I searched up, and then there was some correspondence.
I've been searching for it for a while.
There was some correspondence between Pearson and Fisher, and they talked about this, but there was no source.
Well, I mean, this is typical of one of the examples that Fisher would have worked on at Rockhampton. But that's about as far as I can get. Whether it was one of the examples Fisher worked on at Rockhampton, I have not been able to confirm it. But, yeah, that's not the point. The point is I wanted to have a look at the stuff on experiments. I wanted to have a look at the data and think about these data. Who's done the design of experiments and surveys course? Well, it might be me this semester, so if you survive this with me, then maybe come and do that, but do the experiments with me as well. Okay. So, everyone's fair game for this. I was going to exclude people who have done the design experiments course from answering this next question. What's the response variable here? What's the research question? The two are closely linked.
How we use response to the treatment differentials.
Yields. Yields the response variable. And so, which of the experimental treatments produces the best yield? Is almost certainly the response, the research question underlying this experiment. Okay. What are some of the, again, if you've done the design experiments and surveys, course experience from this, who can lead me through the basic tenets of experimental design? What are the three key things we should be worried about in designing an experiment? Control? Control is one of them. Let's use it for three. I'm looking for a different one first. Randomization is number two. We're getting in the reverse order here.
Factors outside of the control that could affect the yield.
That's a repeat that.
Factors outside the control that could affect the yield.
Yeah, well, that's an issue of control. It's this replication. So if you actually read the Dodson Montgomery stuff, the three R's are replication, randomization, and control. Did I ever start with R? Sorry about that. Okay, so replication basically means that we observe enough of each of the different treatments that we can say something about variability within the treatment. Okay? And we actually have each of the treatments here, they've got six replications of them. We've got 6 different plots planted with the same number of corn plants, and we've measured the yield of each of these corn plots. So replication is how many times we've repeated the experiment. We've repeated each of the different 4 possible treatments 6 times. We have 6 replications here. Because we've got 4 treatments, we actually have 6 times 4, 24 observations. Okay, so those are the 24 observations. Those, if you like, are the treatment averages. And yes, we're going to model things in terms of those treatment averages somehow. And models are going to explain those in terms of those. Notice I said down here, randomization I'll get to last. Control's the next thing. There's a difference with the X variables here. The X variables, exactly the same amount of each of those treatments is applied to each of those plots. So we applied exactly 0 fertiliser to all the control groups, or it might be control in the sense that was what we normally supply as fertiliser, i.e. basic water. Most plants don't survive without it. We didn't have anything else which moved the water. In the water for the second, third, and fourth ones there, we added in potassium oxide, nitrogen. Can't remember the four of them. Potassium oxide and nitrogen, potassium oxide and phosphorus oxide, and nitrogen and phosphorus oxide. And we applied exactly the same amount in each case. The thing about the externals here in experimental design is they are fixed or known. That assumption we make in regression models about the x's being known is not an assumption anymore, because we have deliberately controlled it so it's true. Okay? The x's are fixed. Okay, the other thing about control is the point you were getting at, is that we try to control out all unknown but unwanted sources of variability in the model. Okay? So what else could go on here? If these plots were in a greenhouse, we could make sure they get exactly the same amount of water. If they're outside in the field somewhere, then, okay, local microclimate temperatures, rainfall might differ among the plots. Okay? So the basic principles there in experimental design is that what we can control, we do. If we can make sure that all the experimental units get exactly the same treatment, exactly the same combination of treatments, except for the thing we're interested in, the active treatment, we do. And what we can't control, we measure. And we include them in our modelling as a covariate. So if we work doing it outside, and we have a different rainfall, we'll probably measure rainfall in each of the plots as a covariate. Okay? So, and we'll get to that when we get to analysis of covariance models, which is next week's topic. So the third thing was randomization. So the last thing we do is we try to control, it's a form of control, we're trying to control unwanted sources of bias by random allocation, where we can't, if we can't control, we can't measure, we allocate at random. If you like, is the last thing. So we've got 24 plots of land we're going to use for this experiment. We've got these treatments. Which plot gets which treatment will be allocated at random. To avoid things like, okay, that particular corner of the greenhouse gets a bit warmer. So, well, that particular corner of the greenhouse will get allocated at random to one of the treatments. It could be that something that was we knew if it was an effect, a possible effect, we probably should have measured and included it in our modelling as a covariate. But it could be that we just thought, well, we don't know. There are unknown but unwanted sources of variability in here, and we'll try and control for those essentially by wherever we can doing this allocation at random. It's particularly important in things like medical trials, where the temptation is always to make sure the sickest people in your trials get the most active treatment. Sorry, that doesn't really test your drug. Because typically what they like to do is make a drug test totally unacceptable, because if you give them the active treatment to all the sickest people, they may still die anyway. And so you're not going to be able to say this drug was effective in reducing, but it's a very human failing to sort of allocate not at random. So this is one of the things that Fisher was really important in introducing. So we'll talk about Ari Fisher a bit more. He's one of the gods of statistics, but not necessarily a very pleasant man. So we all follow what he did, but we don't necessarily agree with him on everything. But on the other hand, his two books there are definitely, well, they were the foundation for most of the books that you probably still read today in statistics in this sort of area. In case you are interested, this is a fractional factorial experimental design. There are in fact 3 underlying factors that we're actually going on here. That's adding phosphorus, adding potassium, and adding nitrogen. Each of those you can sort of say either is added or it's not added. So they're actually 3 binary factors. How many possible combinations could you have with 3 binary factors? It's actually 8. there's none of the above. There's 2 cubed. So you could have none of the above, which is the control group. We've got that. You could have each of them just occurring once. We don't have those main effects sort of options here, because we don't have just a treatment where just nitrogen or just potassium or just phosphorus is added. And you can have, there's one other that's missing. All the above. Yeah. Okay. So this is why it's a fractional factorial experiment. It's a 2 cubed factorial experiment. We've only got let's say it's a half fraction. And we've got half of it. The designs, this is actually a hint that what we're seeing here is an experiment that's actually from later on in the research process. The experiments are done iteratively. We iterate through different series of experiments. So we've probably decided that most of these things tend to need at least the 2 ingredients at some stage on the basis of previous experiments. Okay. And there's some reason why we've chosen this particular design for this particular iteration. Possibly because we've ruled out other combinations in early experiments. It suggests to me that this is from very late in the process. Okay. Like I said, if you want to go more into experimental designs and why we do things and how we cut corners and how we sort of set up efficient designs in all sorts of situations, that's really the other course on design of experiments and surveys. That's only half that course. The other half is designing proper surveys. Okay, so what do you think we do here? I'm going to fit a linear model to these. Actually, I might get out of R and start up a brand new workspace. Okay, now I'll start R from in here. Always a good idea, and that way you don't have objects hanging around from the previous one. So if you look, my environment is again, so I opened up a pristine area, it's totally empty. There's nothing hanging around that might have been caught T or something else that's going to get in the way. So I'll read in the core data and attach it. Okay, so there we've got 24 observations, and we've really got 2 variables. We've got the yields and the treatment that was applied to those to get that yield. Okay, so our response variable here, our variable of interest, the thing that our research question relates to is yield. Our ordinary expanded variable is treatment, is our treatment indicator, our fertilizer. Okay? But it's categorical. It's not the sort of variables we dealt with in regression modeling. So we're going to have to code this up somehow. Now the nice thing, of course, is that the modern version of R codes it up for you. And so in fact, we're going to be able to throw this in R and then try and interpret what it's done with. What it's actually going to do is it's going to set up a series of indicator variables in that way. A couple of other things about this experimental design that you probably should notice in passing is that it's balanced. All the 4 different treatments have got exactly the same number of observations. That's going to be important when we start looking at sum contrast with these, because then the sum contrast will be the overall mean. Yeah, the intersection that will be the overall mean. It's also a nice feature to have. You know, really, you are trying to, in some sense, these are all equal states you're trying to observe in the same number of times. You should have the same number of locations for each. Doesn't always happen in practice. Sometimes somebody drives a bulldozer into the corner of the greenhouse and you lose a couple of plots. So you've got missing data. Okay, in the absence of missing data, most of the time these agricultural experiments would have been designed to be balanced, i.e. the same number of applications for each treatment. What we're going to here's the yields. Here's the FERTs. Now, there. Okay, and they just correspond like we showed there. We could plot them, so we could do some exploratory data analysis. And this is the bit I hope you've done for yourself. The obvious thing to do is do what we did for a regression model. Is to plot x against y. Oh, sorry, plot in this situation, that's the x, that's the y. So put that on the axis, put that on the y-axis. And here we are. Is that useful? Is it meaningful? What's it given us? It's given a box plot, which is a snapshot of the distribution of those 6 numbers for each of the groups. What do you remember about box plots? They're not means. What's the middle of the box plot? Median. What's the top of the box? This is the third quartile, 70th percentile. What are the boxes? The first quartile? What's the whiskers? Well, okay, it depends on whether they're Tukey box plots or they're somebody else's box plots. So you have to actually look at the definition here. I think these are Tukey box plots. Tukey box plots, John Tukey, he's one called the box and whisker plots. Tukey was a wonderful statistician, and he just sort of spoke difference first of us. Came up with a whole new Tukey stick. A whisker in a Tukey box plot is 1.5 times the interquartile range up to the minimum or maximum of the data. If there's anything outside the minimum or maximum of the data, anything outside the 1.5 times the... So that whisker actually here, because there's nothing outside there, that's gone to the minimum of the data. That's gone to the maximum of the data. And the same thing on those ones there. Because basically, those whiskers could be 1.5 times the length interquartile range, but they only go as far as the data goes, if you like. If there's anything outside 1.5, there's more than 1.5 times the length of the box away from the box, it just shows as a dot. Okay, as a potential outlier. But remember that this description is in terms of medians, quartiles, and whiskers. Now, very hard to mathematically describe. You cannot really produce these things. And the models we're going to fit are going to model things in terms of their means. So in some ways, it's not actually the right picture for the thing we're about to do with these things. So we really probably what we'd like is probably like a mean plot instead. But that's probably what I hope most of you would have found. Okay, here's the one-way analysis of variance model. Notice it looks like a model. I am telling it to treat FERT as a factor variable. This is what the trick does. And I'm going to feed it to the AOV modeling object. You've never come across that before. It's actually just the LM modeling object in a different disguise. Really all it's going to do here is fit LM. But because we tell it to fit AOV, it actually uses slightly different output. If we use AOV, the assumption is we are analysing a design experiment, and we want certain bits of output. Okay? But actually really what it's doing is LM in the background, and yields our response, and this FERT, forced to be a factor variable, is going to be our x variable. So, if we fitted LM, we should be able to plot it. There's our residual plot. So that's a plot of our residuals versus our fitted values. Why does it look like 4 groups? Because our x variable's got 4 groups. Okay? And so, in fact, there should be 6 observations in each of those. I think there might be, oh no, there's 6 in every single one of them. That means the values are different enough that we can actually see them. Every so often you'll get 2 of them appearing as a single lot. Well, really we've got 6 groups there. 4 groups there of 6. We can see all 24 observations there. Is there a problem with independence? Well, probably not. I mean, what it's doing here really is the model, which is the 0 line here, is actually joining up the means of the 4 groups. And in fact, you can tell where the means of the 4 groups are located because that's the fitted value is that mean. Okay? What's the other thing we should try to be able to assess from a main residual plot? We should be able to assess variability. Are these 4 groups equally variable? This one looks a little more variable than the others, doesn't it? And in fact, of course, R by default will always highlight the 3 most extreme observations on the plot, unless you change that default. And so it's highlighted 1 and 2 at the bottom and top end of that second group. Now, 1 and 2, guess which group that is? That's the first group we had, and the group that is the control group. Okay. It's also highlighted 15, but that doesn't need to be extreme in the same way as 1 and 2 are by each shape formation. So don't always trust the R default. Okay, normality is probably not much of an issue. Again, 1 and 2 are looking a little bit outlying at either tail, but you've got to always say there's only 24 observations here. How normal do you expect things to look? There's a limit with small sample sizes. I'm not going to talk about that plot even in this context. And in fact, because I used AOV, I get this plot rather than my usual outlier plot. This is actually a treatment means plot with standardized residuals, and that's quite nice, because suddenly I can start interpreting the scale on the residuals. Okay? And the suggestion that these are outside plus or minus 2 suggests that we might have an outlier problem. And more than 2 standard deviations away from the mean for that group. Again, we'll have to work out how the standardization is done before we can properly interpret that. Now, if you want all the details of these sort of things, you have to start drilling. Here's the help file for plot.lm, because that's actually what's doing the work here. Notice, by default, we get 4 plots. 1, 2, 3, and 5. There is actually a plot 4, and there is actually a plot 6. If you can work out what plot 6 is, I actually spent hours talking to the bloke who wrote the plot. I'm still no wiser as to what it's actually trying to show me. I talked there with John Mangold. He's the author of the plot.lm stuff. Plot 4, the missing one, is a Cook's distance plot. It's occasionally quite useful. So we'll come back to that. In the comments here, I run you through what each of the 4 plots are, basically. Really, what we're trying with the plot 4 for LM and for AOV are slightly different, because everything has the same leverage, in a balanced experimental design. And so it's actually trying to plot something a little bit more in that situation. So we reduce into a problem with 2 outliers. Let's ignore that problem for the moment, because we haven't really gone about how we're going to treat outliers yet. And we'll just steam straight ahead. So if this problem is ignorable, I'm not saying it is ignorable, What does this tell us? What it's suggesting,
There is a significant difference between
the difference between the factors, so notice there's 3 degrees of freedom there. It's had to code up those 4 different groups. It's actually had to code 3 indicator variables in the background. So it's taken 3 degrees of freedom to do that. So coding up this categorical variable with 4 levels has actually taken 3 degrees of freedom. That's the first time we've seen a variable that takes more than 1 degree of freedom just to sort of feed into a model. All our regression models, we just needed 1 degree of freedom for the slope coefficient. And the interpretation of that slope coefficient was that as we went one in that particular direction, that was the expected change in y as we held all the other x's constant. Okay? We need more than one, for a categorical variable, we need more than one of those sort of slope coefficients. We actually need 3 of them.
So the first one is just the reference level for the other three.
Well, we'll get to the coding in a second. We don't see the coding here. All we see here is an overall test between the groups. So when we get to the summary table, we can start sort of trying to sort of work out what's going on with the code with the levels. Okay, so what do you reckon this F test is telling us?
the difference is significant.
Well, yeah. I mean, what do you think the null hypothesis is here?
The mean of different levels are the same.
Yes. So the null hypothesis here will be that mean for group 1 equals the mean for group 2 equals the mean for group 3 equals the mean for group 4. Okay? The alternative hypothesis is not all the means are equal. Doesn't tell us which one's different. Doesn't tell us where the differences lie, which is what you're getting at. It just tells us that there's no that there are differences between the means, because we would that's a very small p-value. That's a large f value on 3 and 20 degrees of freedom. We would accept we would reject the null hypothesis and further the alternative, and conclude the means differ, if we were happy that this is an appropriate test to do. Notice this business about starring is something that happens in R. I'm not sure I totally agree with it. I do think you probably should have made your decision on what the alpha was going to be a priori. Okay, you should have decided that you're going to use an alpha of 0.05 and just decided that that was going to be, if you're actually going to use this in a decision fashion, you should have made the criteria for the decision before you start, or before you look at the results. Starring things is sort of saying, well, okay, if I decide my alpha is 0.005, then this gets gone. But if I decide my alpha is 0.05, we've got a big gone. Okay, Fisher on these sort of things would sort of say that we interpret these p-values as being more of a measure of the evidence for that for or against the null hypothesis. Well, R hasn't made that choice. R is dodging the choice by basically sort of saying, if it stars, so, well, here's what R is saying, is if I give it 3 stars, it's basically, U alpha is practically 0. If it's 2 stars, then it's, well, it's less than 0.001, it's not. It's actually 0.004. So again, I must admit I haven't spent too much time looking at those stars. I think that probably should have, so 0 is there, not there. Okay, so yes, 0.01 is a 1. Yeah, that doesn't look right, does it? Yeah. I think it must be that you got that, and then you get anything between that and that gets that. Anything between that and that gets that. Anything between that and that gets that. Anything between that and that gets that, and so on. it's the way it's actually supposed to be. Because I know that it does basically anything that's less than 0.05, but it's not bigger than 0.1 will get a star. And yes, I was basically using that to dodge the issue of what should your alpha be. Okay, so the next thing we should do is, well, first thing to note is that I didn't need to put facts around the fertiliser because the fertilisers were coded as characters. It's obviously a categorical variable with name tables. And so the factor thing, it will work its way through that. It doesn't need to tell us a factor. It will treat it as a factor. So if I did this, I would get exactly the same model. So same plots as before, i.e. same model. And same summary. Notice when I use summary on an AOV object, it assumes that what I want to see is the analysis of variance table, not the parameterizations, the coefficients. Because really, as far as Fisher is concerned, this is why the F-test is named after Fisher. What he's really concerned about is there a difference? If he's done the experiment right, he should be able to say what those differences are likely to be before he starts anyway. He's more interested in is there a difference or isn't there a difference? He's interested in this first test at the right level of significance. Notice if I set it up as a linear model, I still get exactly the same plots. But now when I go, if I want to get the analysis of variance table, I have to actually ask for it with a linear model by asking for the ANOVA command. And if I go summary, what do I get? With a linear model, I get the coefficient summary. Okay. And then that's what we have to worry about. How is this parameterized in order to work out how can we get back from those to the various group means? I don't think I've been wasting time because I don't think I'm going to get to that today. Notice if I wanted to get the same thing out of an AOV model, I have to ask for summary.ln of the AOV model. So, in other words, I can get exactly the same information and use AOV or LN because really I'm just doing the same thing in slightly different disguises. AOV exists because basically somebody sort of said, well, we should have a different one for when we fit experimental designs. But really, we actually are doing the same thing.
So if you do use LN instead of AOV, you have exactly the same result.
Well, you have exactly the same. If I've done both just in front of you there.
Yeah.
And I've got exactly the same plots in both situations because I really am doing the same model.
But the whole way through will matter.
Well, if you, yeah, I mean, I suspect for most of us, of course, I'm going to stick to LN. AOV already comes up in this, in these early ones where we are dealing with analysis of variance models without covariance in them, because really they're the ones you should be interpreting as design experiments. But, it's not a. I'll put you through enough examples in the tutes and the like that you'll appreciate the minor differences there are. Working through this one again and working through it with reading the mathematics in the brick is probably a good idea as well.
Is it just there for backwards compatibility with S+? Is it just there for backwards compatibility with S+?
Oh, well, I think that's what the help file says, but I think that's a retrospective justification. There's usually two ways of playing things. One where you set out how you can do things properly, and the other one where you decide you can justify things post hoc. And I think whoever at the help file was justifying things post hoc. Okay, so we need to sort of try and think where did these things come from? Well, the nice thing in the current versions of R is they use the most sensible coding. The most sensible coding is dummy variable indicator coding. Unless you tell it to use some coding, because that could be so it depends on what the search question is. The research question, what do you think the research question here is? Is it a matter of, do we want to compare these treatments with some overall mean, or do we want to compare these treatments to the control group? We want to see if any of the active treatments, how it compares to the control group, first off. We want to make sure that putting some fertiliser on has made at least a positive difference compared to the control group. So the sensible thing in that one is to sort of set up the control group as the reference group. And we've done that by basically making it the first in alphabetical order. Because C starts before K or one of the other ones, it's going to be set up as the reference group. So when you actually see the contrasts that are being used here, this is a series of indicator variables that's set up. Notice it hasn't got an indicator variable from the control group. So for the second group, it's got an indicator variable that indicates we're at the second level, and it's 0 if we're not at the second level. For the third group, we've got an indicator variable that's 1 if we're at the third level, and 0 if we're not. And the fourth level, we've got an indicator variable that says we're at the fourth level. It's 1. If we're not at the fourth level, it's 0. How do we know? What are each of these variables going to be set to for the control group?
The variable, X variable measures.
Well, there's a reason we don't have all four of them. We don't have a control group as well. The control group one will be set to 1 with 3 zeros for the other groups. But we don't need to put that one in there, but we can still work out from the 3 we've got which observation is in the control group. If all 3 of these indicator variables are 0, that means we're not at any of the other levels. So which level must be out? We must be at the control level. And that's how you work out what the reference group is. It's the one for which there is no indicator variable. It's the one basically that we don't have an indicator variable for. And all these others are basically set up to decide whether or not we've got differences between that group and the group we're talking about and the control group. So, what do you reckon this mean is? It's the mean for the control group. This is how much you have to move away from that mean to get to the mean for this group. This is how much you have to move away from that mean to get to the mean for this group. And this is how much you have to move away from that mean to get to the mean for that group. Here's the means. That's the overall mean. Doesn't appear anywhere. Here are the level means. So, this is standard treatment coding. We've got those 3 indicator variables, and what we've done is set up in such a way that the intercept is going to be the mean, the overall mean for when we're none of the other levels, when all the other indicator variables equal 0.
Yeah, we can always change the reference level according to the research question we have.
The reason, yes, and the reason we've got the things the way we want at the moment is because you notice how the means are organised in alphabetical order. The default in R is to set up the first one as the reference group. And only because we were lucky and our first fertilizer treatment started with a C rather than a K or an N, it came first. Okay. If it hadn't come first, and we wanted to sort of compare things to the control group, we'd probably have to do some recharacterization. But you're jumping ahead a bit there. Okay. I want people to appreciate, first of all, that the way we get these means is 72 plus 23 is 95, 72 minus 6 is 66, 72 plus 11 is 83. Make sense? Some very tired-looking people in the back No, okay.
Okay.
What I will do is I'll actually talk you through some of the mathematics for this tomorrow. But a good idea in the meantime is to maybe have a look at this example in R. There's a whole lot of stuff to go yet for us to finish. We'll do that tomorrow, and I'll also talk you through the 6 pages of maths that you do. It's not a mathematics course, in the sense that I said that I expected to actually go along with it. I'd like to appreciate how it's done with this kind of advice. Not that the description is just described in a different way. Just a second.
Okay, I thought you haven't heard me. You wanna log out?
T-apply. Go help T-apply and read the help file.
Oh, okay. And the next question is, I'm not sure what about the construction you're gonna take. Like you take us how to code and explaining about the outputs during the lecture time and practice that in the
Well, if
workshop.
you really want to ask me questions, I probably should make a time and come and see them in my consulting hours, because seriously, with this much noise going on and the way the amount you move your lips, I can't understand a word you say. Okay? See, I can lip read, but I can't lip read you at the moment. And I've made it pretty clear that I don't like being pigeonholed in this situation. I am deaf. You know, so if you really want, you know, we can go somewhere quieter and I can answer. But I prefer not to do it now. I do have consulting times tomorrow. Okay.
Is that the level you're going to teach this class?
现在就是讲课了4个相关的考试4个概念不一样，他明天就要讲，是在其他3个这个就不一样了。因为有现在有4个概念，我们现在学过的只是我们4个人的评述一不一样的这个假设，但是他下个说你们都要来解述我以后一不一样，他要教的是这个。
Yes.
And so really the GLM stuff starts with 2. But yeah, the first few weeks are basically for someone who's actually done a regression course where they did the it's complicated revision for you there. But the first assignment is, you know, it's making sure that you can do those sort of models with our in the context of GPG.
Are you assuming people know how to math? So we are deriving into
every so often I'll show you how to get from what you know from A to B, because it's a useful thing to do. And it's a case of doing something you need to do yourself. But no, I mean, people don't have the algebra.
It's not theory course in GLM.
No.
It's how we use this function.
Mostly the emphasis ends up on correct interpretation of the R output. You know, in that sense, it's ultimately going to R. So, I mean, a lot of this stuff I just have to leave to R and in the later ones, because I just don't. They come to me from maths and finance backgrounds and not from finance. Yeah.
Thank you.
post the lecture sort of thing. So if you've got any questions, have a think about it.